In the beginning of Mod 9, we first want to look at remembering the Pythagorean theorem. X squared plus y squared equals z squared, where x and y are the legs of the right triangle and z is the hypotenuse of the right triangle. If we have a right triangle within a circle, we can replace z squared with r squared because now the hypotenuse is a radius. So now the Pythagorean becomes x squared plus y squared equals r squared. Now we're going to do some algebra and divide all of the terms by r squared. If we use the definition of sine and cosine and simplify the last term, we now have cosine squared because x over r is cosine, so x squared over r squared is cosine squared. Y over r is sine, so we have plus sine squared equals 1. This is what is known as the Pythagorean identities. We can write these identities in other forms, and so we are going to look at that next. Typically, the basic Pythagorean identity with sine and cosine is written with sine squared first. It is not wrong to have cosine squared first, as we had up above. So sine squared of theta plus cosine squared of theta equals 1. We can write this in alternative forms just by solving the equation for either sine squared or cosine squared. For example, we could say that sine squared theta equals 1 minus cosine squared theta by subtracting cosine squared from both sides. Now the third possibility for this identity is to subtract sine squared from both sides, and you would have cosine squared theta equals 1 minus sine squared theta. Now that we know the three versions of the sine and cosine version of the Pythagorean identity, we're going to look for the other versions. I'm going to start with the basic of sine squared plus cosine squared equals 1. If I take this identity and divide all of the terms by cosine squared, well, sine over cosine is tangent, so sine squared over cosine squared becomes tangent squared of theta. Cosine squared over itself is 1, and 1 over cosine, remember that's the reciprocal of cosine, so that would be secant squared of theta. So this is our second possible Pythagorean identity. It too can be written in alternate forms by solving it differently. One alternate form would be tangent squared theta equals secant squared theta minus 1. And the other alternate form would be 1 equals secant squared theta minus tangent squared theta. Now we're going to do the same idea. We're going to go back to the original of sine squared theta plus cosine squared theta equals 1. And this time, instead of dividing all the terms by cosine squared, we're going to divide all the terms by sine squared. Well, sine squared over sine squared equals 1. Cosine over sine equals cotangent, so cosine squared over sine squared is cotangent squared. And 1 divided by sine squared means the reciprocal of sine squared, which is cosecant squared theta. So this is your third version of the Pythagorean identities. Just like the other two, we can solve this and get different versions of it. So the first version is 1 equals cosecant squared theta minus cotangent squared theta. And the second version is cotangent squared theta equals cosecant squared theta minus 1. What helps me remember on these other formats of the Pythagorean identity, which ones go together, is that the co-functions go together. So cosecant goes with cotangent as an identity. This screen is just a list of all the identities that we have. The reciprocals, the quotients, and the even odds we have already talked about. They are just retyped out for you here. And then the Pythagoreans are the newest ones, and they are on the bottom. You do not have to have any of these memorized. When it comes time for a quiz or a test, I will give you a formula page. On example 1, we are told to simplify. Use algebra and fundamental trig identities. Your answer should be a number or a single trig function. The first problem we're going to do is cosine of x times secant of x over tangent of x. Remember that secant is 1 over cosine. And we still have that over tangent. But when I take cosine times 1 over cosine, that equals 1. So we are left with 1 over the tangent of x, and that is cotangent of x. On example B, we have the quantity of 1 plus cotangent squared times cosine squared. One of the things that you need to look for when you are doing this kind of problem is when you have squared trig functions, is there a Pythagorean identity in there somewhere? And when we look at this quantity, that is one of the versions of the Pythagorean identity with cotangent and cosecant. So we can rewrite that quantity as cosecant squared of x times cosine squared of x. Now, as a general rule, you want to change things into sines and cosines if you can't think of anything else to do. And you need to recognize that cosecant squared is the reciprocal of sine squared. So this is going to be equal to 1 over sine squared of x. I'm not going to change the second part of this because it's already a cosine. Now, technically, this is cosine squared over 1. And if you do your fraction rules, you will get cosine squared of x over sine squared of x. Well, that equals cotangent squared of x. Now we are down to a single trig function, so our answer is complete. On example C, in looking at this, we do have a bunch of squared functions, but as it stands right now, none of this is actually a Pythagorean identity. But notice that the first term has a cosine squared, and so does the second term. So we are going to factor out cosine squared of x. If we do that, from the first term, taking cosine squared divided by cosine squared, you're going to be left with 1 minus From the second term, you will be left with the sine squared of x. Now you need to notice that this is one of the versions of the Pythagorean identity. So we are going to rewrite that using what it equals. It equals cosine squared of x. Well, now I have cosine squared of x times cosine squared of x. That equals cosine to the fourth of x. And that would be your answer. We talked about cofunctions earlier in the semester, but as a reminder, I have put them up here for you. What you need to remember is that the functions that are cofunctions will have the same word in them, but one of them has co on the front. So sine is a cofunction to cosine. Tangent is a cofunction to cotangent. Secant is a cofunction to cosecant. They are related to each other because the sine of x is the cosine of 90 minus x. This comes from when we talked about right triangles earlier in the semester. And then conversely, if you know the cosine of x, then you can figure out the sine by doing 90 minus x. Hopefully that jars a little bit of memory for you. On example 2, we are asked to rewrite an equivalent expression by using cofunctions. So if the function that we are given is cosine, like on example A, its cofunction is sine. And to find what angle we need, we should do 90 minus 42. Well, that comes out to be the sine of 48 degrees. On B, if our function is secant, then its cofunction will be cosecant. To find the angle, we take 90 minus 53, which will give us the cosecant of 27 degrees. On example 3, we are asked to prove the identity. On A, our identity that we are asked to prove is that the quantity of 1 minus cosine squared times secant squared equals tangent squared. When you are proving an identity, you are trying to show that you can make one side equal to the other side. Generally, we want to work on the more complicated side and try to make it equal the simpler side. And in looking at this one, the left side is clearly the more complicated side. So I'm going to look at this left side and see what I notice. Hopefully you all see that in this parentheses, that quantity is one of the Pythagorean identities. So the first thing I'm going to do is take that and rewrite it as sine squared of x. Another thing that you want to do frequently is rewrite the functions as sines or cosines. So when I look at this secant squared, I remember, wait a minute, that is the reciprocal of cosine. So I'm going to rewrite the secant squared as 1 over the cosine squared of x. And we're trying to get this to equal tangent squared. Well, if I use fraction rules, if I take sine squared of x, which is technically over a 1, and multiply those fractions, taking the top times the top and the bottom times the bottom, I get sine squared of x over cosine squared of x. We always write equals when we finish to say that we're still saying this equals the other side. But what do you know about sine over cosine? It's tangent. So sine squared over cosine squared is tangent squared of x, and that equals tangent squared of x, so our proof is complete. On example B, we are trying to prove that sine squared of x minus cosine squared of x equals 1 minus 2 cosine squared of x. On this one, I wouldn't necessarily say that one side is more complicated than the other. But when I look at the right side, the only function on the right side is a cosine squared. So what I'm going to do then is work on the left side and try to get rid of the sine squared and make it into a cosine squared somehow. We know from the Pythagorean identities that sine squared equals 1 minus cosine squared. So I'm just replacing sine squared with what it's equal to. Now finish writing your left side. You're going to have minus cosine squared of x equals, well, now look, I have negative cosine squared, negative cosine squared. If I combine my like terms, I have 1 minus 2 cosine squared of x, which equals what we had on the right side originally, so our proof is complete. On example C, we want to prove that the secant squared of x plus the cosecant squared of x equals the secant squared of x times the cosecant squared of x. Again, there isn't particularly one side that's more complicated than the other. And when I look at these functions, I have secant squared and cosecant squared. They are not in a Pythagorean identity together at all. So trying to use a Pythagorean identity will not help me here. So then the other fallback to try is let's rewrite them using sines and cosines. I know that secant squared can be rewritten as 1 over cosine squared. And I know cosecant squared can be written as 1 over sine squared of x. So at this point, this is all still equal. It's just looking different. When you are adding fractions, remember that you have to have a common denominator. If your denominators are completely different, then your LCD is the two denominators multiplied by each other. So our LCD is going to be cosine squared of x times sine squared of x. What that means for the first fraction is that we need to take it times sine squared of x, top and bottom, and then for our second fraction, we need to take it times cosine squared of x, because that's the part of the denominator that's missing. Now we're just going to do algebra and follow fraction rules. Sine squared of x times 1 gives me sine squared of x over, multiplying the bottom, you'll get sine squared x times cosine squared x plus, on the second fraction, 1 times cosine squared gives you cosine squared x over, the denominator is sine squared x cosine squared x. Well, now, since we do have common denominators, fraction rules say add your numerators, leave the denominator alone. So it will become sine squared x plus cosine squared x over sine squared of x times cosine squared of x. Now, hopefully, this numerator is jumping out at you. Sine squared of x plus cosine squared of x equals 1. So we have 1 over sine squared x times cosine squared of x. So it took a lot of work and we got it down to a much simpler fraction, and look at where we're trying to go. We're trying to get a secant and a cosecant. And those are the reciprocals of sine and cosine. So a little fraction trick, and this is just fraction rules again, is that we can split that one fraction into two fractions that are 1 over sine squared of x times 1 over cosine squared of x. But I know that 1 over sine squared equals cosecant squared of x, and that 1 over cosine squared equals secant squared of x, and that equals what we were trying to get to, which was secant squared of x times cosecant squared of x. And we have reached our proof. On example D, we are asked to make cosine of x over 1 plus sine of x equal to secant of x minus tangent of x. In this one, I would consider the fraction to be the more complicated side. And right now, looking at this, we have no squares anywhere. So we don't have any way of using a Pythagorean identity. But there's a little trick that we are going to do. We're going to leave the fraction on the left side as is right now. And then we are going to take it times the conjugate of the denominator. You have done conjugates before in radicals. In a term like this, it's going to be the same items, but you change the sign. But whatever you do to the bottom of a fraction, you want to do to the top of a fraction. This means that we are taking the fraction times 1, so we are going to make it look different, but we're not changing the value of it. So we're not going to do anything to that numerator except just write it as cosine of x times the quantity of 1 minus sine x. What we are going to do for the denominators is use FOIL. So in our denominator, we will have 1 minus sine of x plus sine of x minus sine squared of x. Well, looking in the middle here, negative sine, positive sine equals 0. So now we still have our numerator as it was originally. And our denominator simplifies to become 1 minus sine squared of x. Now we do have a squared that is a Pythagorean identity, so we are going to replace that denominator with what it's equal to. So we're going to have cosine of x times 1 minus sine of x over cosine squared of x. Well, now I can simplify the cosines. I'm going to take out the one that's on top and one of the two that's in the denominator. So now I have 1 minus sine of x over cosine of x. Again, we're falling back on fraction rules. we can rewrite that single fraction as two separate fractions that are 1 over cosine of x minus sine of x over cosine of x. What do you know about 1 over cosine? It equals the secant of x, and sine over cosine equals the tangent of x, and that's what we were trying to get to. So our proof is complete.